Hello students, welcome to my channel Explore Organic Chemistry with Anjali for UG and PG students. Today I am going to start with the pericyclic reactions and today's lecture is the introductory lecture. So as we see that before pericyclic reactions, mainly organic chemists they used to talk about the ionic and the radical reactions. As we know various organic reactions SN1, SN2, E1, E2 and so many other reactions. We know that those reactions they follow the ionic and radical reactions path. Now these are the reactions, they are completed through the formation of ionic counterparts or ionic transition states, or we can say the ionic intermediates. And those intermediates they are like carbocations, they are carbocations, they are carbanions, they are carbanions, or in some cases they can be free radicals. And we know that all the reaction mechanisms it has many steps, that is initiation, propagation and termination. So for initiation we are using various catalysts, we are using various reagents, etc, etc, and then we form the carbocations, carbanions and free radicals as a intermediates. Then we can achieve the formation of the product. So this is the overall, like we have reactants over here. These are the reactants and we are using some parameters, some heat or some reagents are required. They gives you some intermediates that we know that those intermediates, as we have seen, that they can be carbocations, they can be carbanions, or they can be free radicals. So via formation of intermediates then we can achieve the formation of products, and this involves various mechanisms, various steps in the mechanisms, as we know that the initiation, propagation and the termination of the reaction. So what is the strategy of pericyclic reaction? Of course it is a organic reaction. Why it is an organic reaction? Because the pericyclic reaction also helps, pericyclic reactions they also helps in the formation of carbon carbon bond. So whenever the reaction forms a carbon carbon bond, it can be a organic reaction. So it has a very significant value in the organic synthesis. Now what differs these reaction from the other organic reactions? So what is the difference between pericyclic reactions and the difference between pericyclic reactions and organic reaction? Now here the main difference is that the reaction is called as pericyclic reaction. So the name itself suggests that there is something cyclic in the complete mechanism or complete the reaction. So what are pericyclic reactions? Let us see some significant features. So what are pericyclic reactions? Let me define. What are the pericyclic reactions? Now here in this case, let me define that the reaction takes place in a concerted manner. So here I am writing the definition. The pericyclic reaction takes place via concerted manner or through concerted manner, takes place via concerted manner. Now what is the meaning of concerted manner, or what is the meaning of concerted? That is, it is a simultaneous bond breaking and bond formation. So here the exact meaning of concerted means the reaction takes place in which the bond breaking and bond making or bond formation both are simultaneous. They are simultaneous in a one step, of course. Simultaneous and but through the formation of cyclic transition state, through the formation of cyclic transition state. So this is exactly the definition of pericyclic reaction, which that it takes place via concerted manner. And what is the meaning of concerted? That the bond breaking and bond making in the reaction, they are simultaneous and they form through the formation of cyclic transition state. Now here, what about the initially it was considered that pericyclic reactions are no mechanism reaction. Pericyclic reaction was considered as no mechanism reaction, but later on the things are revealed that the mechanism is something very different as compared to other organic reactions. So this was further revealed that yes, there is a mechanism, but the methods are different. The mechanism takes place, the reaction takes place via mechanism, and the mechanism takes place via molecular orbitals. So this is something very new we have to learn in this particular topic. All right, now the reaction, as we are talking about the mechanism, so this mechanism, so how it follows, as we know that the mechanism, we have seen the definition that the reaction follows concerted path. At the same time, we can say that reaction is simultaneous but not synchronous. Now let us see the meaning of these two terms. So simultaneous means reaction takes place at that time. So moment is very important over here. At that particular moment where bond breaking and bond making takes place. But synchronous meaning that there might be a same period of time, but there can be a periodic interval. So periodic interval. So this term correlates with the periodic interval, and the simultaneous, this term correlates with the at that moment where both the mechanisms are happening or both the phenomena are happening, that is bond breaking and bond making. Of course, the reaction takes place via formation of transition state, that is a cyclic reaction or a cyclic transition state. So that is why, but this particular terminology is used for the pericyclic. So why pericyclic has been used? There is a reason for that. There is a cyclic shift of electron, cyclic shift of electrons take place along the periphery of the molecules, along the periphery of the, or rather you can say the reactants, or it may be a one reactant, it may be two, it may be more than one. All right, so or you can say that the component also. So various terminologies can be used. So cyclic shift of the electrons take place along the periphery of the reactants, along the periphery of the molecules. One more term I need to add. Thus it is known as pericyclic reaction. Thus it is known as pericyclic reaction. Got it? Pericyclic reaction. So before we go to the actual examples or some important features of the pericyclic reaction, let me revise whatever I have told you just now. That we know that pericyclic reactions, basically pericyclic reactions, they are organic reactions because they also form CC bond. Whenever the reaction forms CC bond, that is called as organic reaction. That please you need remember these things. The another thing is, before pericyclic reaction or all the organic, we know that all the organic reactions, they follow the path that is the formation of carbocations or intermediates. They can be carbocations, they can be carbanions, they can be free radicals. So as we know that reactants, they undergo some changes under the influence of various parameters we are using. Here I can say that these are the reagents, heat, pressure, etc. Various parameters we are using to initiate the reaction, and the intermediates are formed, and finally we can achieve the formation of products. So this is how the mechanism, in general mechanism, we have seen in the organic reactions, that is SN1, SN2, E1, E2, etc. But pericyclic reaction is totally different from the whatever reactions we have seen till date. Now how it is different and why it is different, that is also explained over here via the definition. The definition tells you that the reaction takes place via concerted manner. Concerted means the bond breaking and bond making takes place at the same time. Now here another terminology I have introduced over here, that this mechanism follows the simultaneous way but not synchronous. Actually these two terms are little bit similar, but simultaneous means at the same moment where the reaction shows bond breaking and bond making, whereas synchronous means in a periodic interval, means time may be different, but you can say that this is the at the same period of time you can connect with this terminology. But we are associated with this particular term, that is the simultaneous bond breaking and bond making takes place. Another point we revealed over here, that why these reactions are called as pericyclic reactions, because we have seen that there is a continuous cyclic shift of the electrons along with the periphery of the reactants or the molecules or the components. Thus, they are known as the pericyclic reaction. So, let us see some examples how they can be seen whenever there is a. So, here, so what is the name of this structure? What is the name of this structure? It is a 1,3-butadiene. This is a 1,3-butadiene. Yes. So 1,3-butadiene undergo. Now here later on I will explain you everything why I have put H nu and the delta, because the reactions are thermally induced, the reactions are photochemically induced also. So here I can explain the flow of electrons. Now here some more thing I could show you that. So these are the two electrons. I always tell you that try to find out the electrons. So whenever the reaction has started, the flow of electrons will started moving. Now here the definition tells us that the reaction proceeds via formation of cyclic transition. Alright, so this is a cyclic transitions. So this is a cyclic four-membered. This is a four-membered cyclic transition state. Cyclic transition state. Alright. Okay, done. And then the reaction is moved toward the forward direction where we can get this cyclic structure, which is nothing but the cyclobutene. Now, what is the beauty of this reaction? Here, both things can occur. So, what are those things? What are the highlight and the important point to be noted over here? That closing and opening of the ring can be happen. As I have shown you, these are the two arrows. They are self-explanatory. So, closing and opening of the bonds are possible in the pericyclic reaction. Closing and opening of the bonds are possible. So this is one of the examples I have shared with you, that 1,3-butadiene undergoes either thermally or photochemically. It is going to form this four-membered cyclic transition state. So you can see this is a flow of electrons which shows a cyclic contour over here, and then it leads to formation of four-membered cyclobutene. So the accountability of the double bonds and the electrons I will explain in particular in this whenever I teach the electrocyclic reaction. So this is a electrocyclic reaction. So we will see the brief idea about in next few lectures. So here it is a just a brief idea about the significance of the reaction. So this is one of the reaction. Now another example I can share with you, that here we see, you can see that I have used only one reactant. I have used only, so this is extremely important, that here I have used only one reactant. So with the one reactant I have achieved the product, the desired product, by using this technology or this mechanism. All right. Now another example, I am using the two reactants. I am using two reactants. Again, all the reaction you will see that they are having these two arrows, and those arrows means that they are reversible reactions, or you can go in the backward direction. Here also I am showing you the flow of electrons. They are going to form a six-membered ring. So here also, now let us draw the how the electrons will flow. So here again I am drawing these two electrons. These are the two electrons. So here this is the way the electrons are flowing from one region to another region, and here I am getting the cyclohexene. Okay, so this is also the another reaction which is called as cycloaddition reaction. Of course, we will see later on the details about all these reactions. Right now I am only explaining the concept of the pericyclic reaction. So here you can see that this is electrocyclic reaction where I have used only one component, and here I am using two components where again there is a formation of six-membered ring. Here is a four-membered cyclic transition state. Here is a six-membered transition state. So do not avoid Do not forget to draw the cyclic transition state. If you forget, then the reaction doesn't have any meaning. So transition state is equally important. Without transition state, reaction doesn't proceed in the forward direction. So please remember, whenever you draw the mechanism, you have to draw the cyclic transition state. It is a mandatory. All right, so this is this reaction where I have used two components. So here I can see that how many pi electrons are there. I have 4 pi electrons. Here I have 2 pi electrons. So out of that, here you can see that the number of pi bonds are reduced. Here also the number of pi bonds are reduced. Here we have the 4 pi system, and in the product we obtain only 2 pi. Here we are using 6 pi electrons, sorry, 4 pi electrons. Here I am using 6 pi electrons, and I am only getting 2 pi electrons and one bond. So the products are formed in the cost of exhaustion of the double bonds. The double bonds are exhausted over here in the bond formation, and some new sigma bonds are also formed. So here I can say that the new sigma bonds are formed and one ring is also formed. Alright, here also I can say that the sigma bonds are formed. So how many sigma bonds are formed? Here there are 2 sigma bonds I can see over here, and plus one ring. So here whenever see the detailed mechanism, I will explain all the things, but for the time being, just look into the manner that look into this reaction, that the reaction proceeds via what I am explaining only, how the reaction takes place or how the reaction proceeds via formation of 6-membered ring. This concept I just wanted to share with you. Then let us see the various categories of the so pericyclic reactions. They are categorized into pericyclic reactions. They are categorized reactions are categorized into various types. We just see the types of the reaction. As I told you that I will explain it later on after this introductory lecture. So the first reaction is the electrocyclic reaction. First reaction is electrocyclic reaction. Another reaction is a cycloaddition reaction. It is a cycloaddition reaction. Third reaction is ene reaction. Third reaction is a ene reaction, or you can say that this is a group transfer reaction. This is also called as group transfer reaction. Fourth, actually I should write it on the third position, the sigmatropic, because this is a extremely important reaction. So anyway, so sigmatropic reactions, or these reactions are called as sigmatropic rearrangement reactions because the rearrangement takes place over here. And then the chelotropic. This is a chelotropic reactions. So these are the 5 reactions we are going to study in next few lectures. So let us see one by one. That is the pericyclic reactions. They are categorized into various types, and those reactions are electrocyclic reaction, cycloaddition reaction, and ene reaction, or you can say it is a group transfer reaction, or sigmatropic rearrangement, and the chelotropic reaction. This classification was, now it is very important who investigated or who discovered all these reactions. So this classification was first introduced by This classification, this group of classification, or this group of reaction was first introduced or first reported in 1965. By whom? By R.B. Woodward, R.B. Woodward and Roald Hoffman and Roald Hoffman. So these two scientists, American scientists, they have reported this classification, this group of reaction in 1965. Later on in 1981, Kenichi Fukai and Roald Hoffman, they received the Nobel Prize. They shared the Nobel Prize for these pericyclic reactions. But the one thing I would like to share with you, that Woodward was not the part of this Nobel Prize, because in 1965 he had been awarded with the Nobel Prize in the organic synthesis. So Woodward already achieved awarded with the Nobel Prize in 1965 in his excellent work, in his outstanding work in the organic synthesis. Alright, so this is a brief idea about the classification of the pericyclic reaction and who introduced these classification or this group of reactions. R.B. Woodward and the Roald Hoffman. So in 1981, Kenichi Fukai and Roald Hoffman, they received the shared Nobel Prize for this noble work. And of course, the Woodward was not the part of this Nobel Prize. Alright. Now let us see some important characteristics of the pericyclic reactions. Let us see one by one. They are extremely important, because if you know all these characteristics, then it can be easily solve the problems, or some you can also see the various mechanisms of the pericyclic reaction while solving the mechanisms. All right, as we know that the reaction is concerted, so this is the extremely important characteristic, where all the bond breaking and bond making are simultaneous. So bond making and bond breaking are simultaneous. So I am writing in a brief, bond making and bond breaking is a simultaneous. This I have already explained, and alright, and the reaction takes place via cyclic manner. Another most important characteristic, that there is no role of acid or base in the reaction. So this is extremely important, that it doesn't require any acid or base as a solvent. So no role of acids or base. Alright. So, and what is the third important point, that there is no role of electrophiles, or any nucleophile. It doesn't require any nucleophile. It doesn't require any electrophile or nucleophile. Please remember, or any free radical. So I have already explained that the reaction doesn't follow the classical path, right? It doesn't require any electrophiles, it doesn't require any nucleophile or free radical. It is totally different from the rest of the reaction, that is ionic reactions or the free radical reaction. The mechanism is totally different. So obviously there is no need of the electrophiles or the, so no electrophiles are involved, no nucleophiles are involved, also the no free radicals are involved in the reaction, in the pericyclic reaction. All right, so these are most and most important characteristics. So every characteristic is equally important over here, please note down. Then the another important that, so that's why the reaction is totally different from different from the rest of the organic reaction. Those reaction I can say that the ionic reactions and the radical reactions, means those the reaction they proceeds via formation of carbanions, carbocations, radicals, etc. So it is totally different from all those reactions. So please remember, this is also an important point to be noted. Another most important characteristic is that the polarity of the solvent does not affect the rate of reaction. Have you seen that? The polarity of the solvent. Now what polar solvents we are using generally in the reactions? We are using methanol, we are using water, we are using ethanol, acetic acid. There are so many polar solvents. So if polar solvent does not affect the rate of reaction, so whatever solvents you are using, it does not it does not increase the rate of reaction, neither increases its rate of reaction nor decreases the rate of the reaction. So the solvent doesn't have any role in its initiation or the acceleration of the rate of the reaction. So this is the wonderful characteristics that pericyclic reaction does not require anybody to move on in the forward direction, please remember. All right, so next point, that even no change in the rate, no sorry no change in the rate, no change in the rate in the rate of the reaction by the addition of added salts, by the addition of added salts. Sometimes we need to add some added salts to accelerate the rate of reaction. In some organic reaction it requires, but here there is no need to add any added salts. So please remember that even added salts are not required to initiate the reaction or to accelerate the rate of reaction. Likewise, then also no radical initiators, no role for, there is no role for radical initiators or quenchers. Now we have seen in the photochemical reaction that benzophenone is a photosensitizer and it is used for the sensitization of the reactants so that we can proceed the reaction via formation of radicals. So in this case, in pericyclic reaction, there is no role of the radical initiators as well as the quenchers. All right. So the pericyclic reactions, they occur thermally and photochemically. All right. If it takes place in thermal condition, it is called as thermally induced. or if it takes place in the photochemical conditions, it is called as photochemically induced. Also, no reagents, no use of reagents, no use of reagents in the pericyclic reactions. Alright. So these are 9 characteristics. Let us see again. I am again revising this thing. The reaction is concerted, where bond making and bond breaking is simultaneous. It doesn't require any acids or base to make the reaction move in the forward direction. The third and most important point is no electrophiles, nucleophiles, free radicals are involved in the mechanism. So please remember, whenever you run any mechanism for the pericyclic reaction, do not put such things which are not formed, which are not required in the pericyclic reactions. That's why the reaction is totally different from the ionic and the radical reactions, as I have explained earlier also. Similarly, in many organic reactions, we have seen that if we change the polarity of the solvent, the rate of reaction may increase. If we change the polarity of the solvent, sometimes the polarity may decrease, or it may decrease the rate of reaction. But here the polarity doesn't work over here on the rate of reaction. So there is no role of any polar non-polar solvent to affect the rate of reaction. Then the next point, we have seen that there is no change in reaction, rate of reaction, by the addition of added salts. Then the role of radical initiators and quencher is also there. The reaction, of course, initiated by thermally and photochemically. If it takes place thermally, it is called as thermally induced reaction. If it takes place by photochemically, it is called as photochemically induced reaction. Alright. So here again, there will be no reagents are required, no use of reagents are there in the pericyclic reaction. Also, one more important thing I forget to write, that no catalyst is also required. No catalyst. No catalyst is required. Only in Diels-Alder the reaction required. Diels-Alder, of course, is a pericyclic reaction. So dear students, only in the Diels-Alder reaction it is affected by catalyst. So Diels-Alder reaction is affected by catalyst. Otherwise, the rest of the pericyclic reactions do not affect by the catalyst. Catalyst doesn't have any role, doesn't play any role in the mechanism of the pericyclic reaction. Then the most important point is that pericyclic reactions are stereospecific. Pericyclic reactions are stereospecific. We know that specific. So we have already seen the stereospecific and the stereoselective. So stereospecificity is the important, but here, for example, if the reaction takes place, so these are the reactants, suppose, and this is, it takes place by thermally, so you will get some A result or A product, or the same reaction takes place with the photochemically, you may get B reaction. So that the stereospecificity is maintained over here. You can't, if you get A over here, the reaction will become stereo selective. But here both the reactants are same and you are getting different products. It means that by changing the reaction conditions, so the reactions are stereospecific. We will see later on one by one. Then the next characteristic is the symmetry of the orbitals. Now this is the most important. The symmetry of the orbitals is conserved. The symmetry of the orbitals, as I told you, that the reaction mechanism proceeds via the molecular orbitals or linear combination of atomic orbitals, as I told you. So the reaction doesn't proceed via the formation of any intermediates, but it forms via the interactions of various atomic orbitals and the molecular orbitals. So symmetry of the orbitals of the reactants are involved. And what is the role of reactants and the products? Yes. So symmetry of the orbitals of the reactants and the products is conserved. Conservation of symmetry takes place while the reaction proceeds from one step to another step. All right. So here we will see detail about, because the pericyclic reaction is nothing but the rest of the things are okay, but we are dealing with only and only this particular point, that the mechanism takes place via the interaction of the molecular orbitals of the reactants and products. So we will explain the details in the next lecture. So let us see the next feature of this extremely important aspect, that we know that both delta and h nu, they are the energies. They are the energies. But this energy term is not sufficient to explain the mechanism, because delta is the different source and the photochemical photolysis is the different source. Both the energies are the different sources. So how the reaction takes place in this, it means only energy is not sufficient to explain the results, but it is important to make a difference between these two reactions. How? Thermally and photochemically. So I can mention over mention here that the thermally induced reaction will give you the only vibrationally excited ground state. Vibrationally excited ground state. This is the difference. You can see vibrationally excited ground state. All right. And here in the photochemically, what is going to happen? Photochemically, here if you give hit to the reactants, what is going to happen? The molecules or the atoms, they vibrationally excited in the ground state itself. There will be no excitation. They will remain in the ground state, or they may remain in the bonding orbitals. But in the photochemically induced reaction, what is happening? The reaction takes place through electronically excited state. Electronically excited state. So I have already explained what are the electronically excited state: singlet state, triplet state, ground state. So these are the photochemical reaction takes place via electronically excited state. All right. So here a little bit idea I would like to show with you, that so when the reaction, so suppose this is your container and you are heating the reaction mixture. So here I can show you what is exactly happening. So in the ground state, this is the ground state. When you heat this molecule, what is going to happen? There is only the vibration takes place over here in the ground state. So in the thermal reaction, only the electrons, they do not move away from the, so here this this is an anti-bonding orbital, and this is a bonding one. All right. So when you hit the reaction mixture, the electron will stay in the ground state itself. Only the energy will be increased in the ground state. Please remember, energy of the electron will increase in the ground state. Of the electron increase in the ground state itself when the reaction is thermally induced. Now, when reaction is photochemically induced, what is going to happen? So this is the another reaction mixture. So I am inducing, this is the HNO. What is going to happen? Just remember the Jablonski diagram. When the reaction mixture is irradiated with the HNO. So what is going to happen over here? This is the first singlet state. This is the first singlet state, as I already explained. Now I am not going to explain detail about, because I have already teach you the Jablonski diagram. Now here what is going to happen, that we know that according to the Frank unknown principle, so this remain in the alright. So let us check the direction of these two electrons. In the first excited state, there will be no change in the direction of the electron. After intersystem crossing, the electron will change its direction. So here they are anti-parallel, they are anti to each other, and here they are parallel to each other. Now maximum time it was observed that now here in both the cases we can see that this is a bonding orbitals and these are the anti-bonding orbital. So what is the difference between thermally induced reaction and the photochemically induced reaction? This is the major difference, that in the thermally induced reaction, the electron will stay in the ground state. They will stay in the ground state. The electron will stay in the ground state in the thermally induced reaction, while in the photochemically induced reaction they cross the barrier and they move into the anti-bonding orbital. In the ground state, the anti-bonding orbital always remains vacant. They never be filled up. Alright, but in the photochemical reaction, one of the electrons get excited to the higher energy level, that to the anti-bonding orbital, and here you can see that the HNU reaction, the electron goes from bonding orbitals to anti-bonding orbitals. Alright, anti-bonding orbitals. So this is the major difference between the, what you can say, this is the major difference between the thermal and photochemical reaction that I have explained categorically over here. Then another most important thing I need to explain, that as you have seen all the reactions I have drawn over here likewise. So all the reaction they show this type of double the double arrow. It means that these reactions they are they go with the forward direction and the backward direction. So they go with the forward direction and the backward direction. So pericyclic reaction can move in the forward direction, pericyclic reaction can move in the backward direction. So this principle is known as the principle of, this is the principle of microscopic reversibility. Microscopic reversibility. Microscopic reversibility. And then as also I told you that it forms CC bond. CC bond formation is the ultimate goal for all the organic reactions. So obviously in this reaction we are also successful in forming various CC bonds, so it has a significant value. The most important one more thing is it gives high yields. It gives high yields. It gives you high yields. So there will be no side products. There will be no side products. This is the most important. That is the beauty of this pericyclic reaction is it doesn't form any side product or it doesn't form any byproduct. Directly it converts the reactants into the products. Okay, so please remember this is the most important point in the reaction. Now let us discuss. I am giving you some brief idea about the whatever I have explained. I have given 5 reactions. So let us see a brief idea about the electrocyclic reaction. Now what is electrocyclic reaction? Electrocyclic, of course, all the pericyclic reaction, please remember they required what reactants we are using. We are using dienes, we are using polyenes over here. So all your reactants are having double bonds, means pi molecular orbitals are involved in the reaction. So this is the most important statement I am making. In all reactions, in all pericyclic reactions, the main feature that the reactants are polyenes. The reactants are having polyenes or alkenes, or they may have number of double bonds. So we are dealing with the molecular orbitals of the pi bonds. All right. So pi electrons are involved in the reactions, pi bonds are involved in the reactions, pi molecular orbitals are involved in the reaction. The interactions of pi molecular orbitals have been seen over here. So let us see the here what type of reactants we are using. We are using the conjugated dienes. We are using the conjugated dienes over here, and or we can use strained rings. You can see various miracles in the reaction. As and when required, I will explain all the conditions, but for the time being, just remember that in the electrocyclic reaction, only one reactant, please remember, only one reactant we are using over here. Only one molecule we are using over here, and that too, they can be a conjugated dienes or they can be a strained ring. Then next thing is ring opening or ring opening or ring closure takes place. It happens in the reaction. So at the here the pi bonds are exhausted in the ring formation, or you can say the product formation. So pi bonds are responsible, or I can say exhausted in bond formation or in product formation. So this is all about the electrocyclic reaction. So let us see couple of examples. I have already given you the couple of examples here. Just this is a 1,3-butadiene, and here, as I told you, that the both bonds are arrows are required because the reaction takes place in the both directions. So this is a cyclic transition state which leads to formation of the. All right. Now here you can another one more example I would like to share with you, that Here is also, so what is the name of this? 1, 2, 3, 4, 5, 6. So it is a 135 hexatrine. It is a 135 hexatrine. This is 1,3-butadiene. This is 1,3-butadiene. Alright, so here H nu, this might be a okay, so I can, here 6-membered ring is going to form. So here double dagger, and here the 6-membered ring. Now let us see the accountability of this particular example. So suppose this is first example. How many bonds are there? There are 2 pi bonds. There are 2 pi bonds. And let us see in the product. How many bonds are there? 1 pi bond. 1 pi bond. 1 new sigma bond. And 1 ring. In the another example, how many pi bonds are there? There are 3 pi bonds. There are 3 pi bonds. And in the product, there is 1 pi bond. 1 pi bond plus 1 new sigma bond. 1 new sigma bond. And plus 1 ring. And plus 1 ring. So this is about, so overall accountability or in the cost of double bond, overall accountability is, if I have n pi bonds in the product, I will get n minus 1 pi bonds plus 1 new sigma bond plus 1 ring. This is the accountability of the electrocyclic reaction. In this electrocyclic reaction, if I have n pi bonds in the product, I will get n minus pi bonds, 1 sigma new sigma bond and 1 ring. So in the product, this is these are the changes we can observe in the product, that n pi will change into n minus 1 pi, 1 sigma bond and 1 ring. Let us see the another type of the reaction, that is the cycloaddition. Cycloaddition reaction. In cycloaddition reaction, again the conjugated dienes are involved. Conjugated dienes. Then again the second feature, that is the ring opening and ring closure is the same feature, but here we involved 2 components, means 2 reactants. 2 reactants are involved. Alright, in the electrocyclic reaction, there is only 1 component or only 1 reactant. Please remember, only 1 component or only 1 reactant is involved in the electrocyclic reaction. But in the cycloaddition reaction, what you can see, there are 2 components which are involved in the. So let us see. I will explain this example. Again, this is a 1,3-butadiene. This is 1 component and this is the another component. Again, I will put a double arrow, as we know that the reactions are reversible. Now here I am getting the 6-membered ring, which is, now overall let us count the number of pi bonds. How many pi bonds are over here? So there are 2 pi bonds and 1 pi bond over here. Means total there are 3 pi bonds. In the product, how many pi bonds are there? Only 1 pi bond. Only 1 pi bond. And 2 sigma bonds are formed. 2 new sigma bonds are formed. And 1 ring. And 1 ring. So overall accountability means in the exhaustion of pi bonds, overall accountability will tell you that what is happening. If in the reactants, if I have n pi bonds in the product, what should I see? I am getting n minus 2 pi bonds plus 2 new sigma bonds and 1 ring. So this is the accountability. These pi bonds are utilized in the formation of 2 new sigma bonds, in which the number of pi bonds are reduced in the products. Okay, so 1 ring has been formed over here. So this is about the cycloaddition reaction. Then the third reaction is the, I'm going little bit fast because in the same lecture I have to finish the introduction part. So the third is a sigmatropic reaction. This is the sigmatropic reaction. What is the beauty of this reaction? The migration of sigma bond. See, the title itself reflected everything. There is a migration of sigma bond from one terminal to another side of the double bond or chain, you can say that. It may be a conjugated, it may be a non-conjugated, or it may be a isolated. There are 3 types of dienes. We know that isolated, cumulative and the conjugated. So here we can use the conjugated dienes, we can use cumulative, we can also use the cumulative doesn't work, but the isolated double bonds are preferable in this reaction. Alright, so here I can say that the migration of sigma bond from one terminal to the another side of the double bond. Now let us see how the reaction takes place. So here what are the important features? That no change of double bond, no change of pi bonds, no change of pi bonds. Means if n number of pi bonds are present in your reactants, in the product the number of pi bonds will be retained or they will be same. For example, n pi in the reactant, in the final there will be n pi. There is no exhaustion of the pi bonds. And also the ring in the reactant does not change in the, so it will be as it is in the ring in the product. So there will be no change in the any double bonds or the ring formation, etc, etc, etc. Only there is a migration of sigma bond. Now let us see how it works. Let us see how it works. Now this is an example. Here I am using this alright, so this is a diene, and here, so this is a deuterated methyl group I am attaching over here. So H nu, it can be H nu, we will see later on how the reaction takes place. Now here how the flow of electron will move, So these are the 2 electrons, So this is sort of intramolecular rearrangement reaction. It looks like a electrocyclic reaction, but in the electrocyclic reaction there is a cyclic formation. Here there is no cyclic formation. So what is going to happen? These along with the electrons, this D will move at the now here I would like to numbering this moiety, because now where do I start? From here or here? I have to start from here. 1 2 3 4 5. Why not this to this? Why not 5 will be 1? Because we know that, so look at this particular structure. This particular structure is nothing but the, so this carbon is the allyl carbon. This carbon is a allyl carbon. So allyl carbon, whenever you numbering the moiety, you should always start with the allylic carbon. This is a sp3. This why this is called as allyl carbon? Because this carbon is sp3 and this is attached to the sp2. So this moiety is allyl moiety and this carbon is the attached to sp2. So this carbon is known as allyl carbon. So whenever you you need to numbering the molecule, you search the proper center. Here I am getting the allylic carbon, so I have started my numbering from the allylic carbon. So always remember how to numbering the molecule, not from this place. I have started with this place. So allylic carbon will be your first carbon. So later on you can see over here. So this deuterated substituent has been migrated at the 5th position. So from 1st position to 5th position. So this rearrangement is called as 1,5 shift. This is called as 1,5 shift. Now as soon as this D moves at the 5 position, you can see that there will be a migration of electrons takes place. There will be a migration of electron takes place. Now let us draw the structure. So as D moved over there, so D dash, and here there are 2 deuterated salts. So these electrons moved over here. So this will be the structure of the molecule. Alright. So here I can say that overall reaction will be N pi, where in the products there will be N pi, there will be no change in the ring, no change in the, of course in this case I have not seen any ring, but this is the overall output of the reaction. So there will be no change in the ring. Then the next reaction is the 4th reaction. This is called as a group transfer reaction. Group transfer reaction. This is a group transfer reaction. The important points to be noted that here also the sigma bond migrates. Sigma bond migrates from one molecule to another molecule. Please remember that in the sigmatropic there is only one component or there is only single molecule, but here in the group transfer there is a migration of sigma bond from one molecule to another molecule. This is the difference. Please note. Another molecule. So this is little bit the combination of 2 reactions. So group transfer reaction may be, if I say that this may be a combination of, this is a combination of little bit, not exactly. This is a combination of cycloaddition reaction and plus sigmatropic reaction. Alright, because in the cycloaddition reaction we are using 2 components or 2 molecules. So that's why, and of course the dienes are using. So the cycloaddition reaction takes the condition fulfilled, and also the sigma bond migrates from one molecule. But here what happens? It moves from one molecule to another molecule, but there is a moment of sigma bond, so I can correlate this reaction with the sigma tropic also. Now let us see the example. Now here I have this allelic carbon, so D is there, plus I have this ethylene, and again the reaction condition. Now what is going to happen over here, that the moment of electrons I can show you that, so these are the 2 electrons, here also 2 electrons. Alright, so as soon as the electron move like this, now the final result will be in this way. So how many sigma bonds are there? So here there will be a formation of sigma bond. So this D transfers over here. So here is another sigma bond. So formation of 2 sigma bonds in the cost of exhaustion of 1 pi bond. So formation of 2 sigma bonds we can observe over here. So overall reaction shows how many pi bonds are exhausted. Here there are 2 pi bonds, here is 1 pi bond, and here is another pi bond. So 2 pi bonds in the reactants. In the product there will be only 1 pi bond, but there will be 2 new sigma bonds, observed. So this is about the group transfer reaction. The mechanism, as I told you, that I will explain one by one all the reactions separately, because this is a introductory lecture, so you should know that what is actually pericyclic reaction is and how it is categorized into various types. Now this is the last reaction I can explain. These are the chelotropic reaction. Now here only single atom forms ring with pi system, some pi system. Let us see the example. What is the example? Example is, now here I have shown you the carbene. Now these are the 2 electrons. So one will move over here, one will move over here, and it is going to form a chelotropic reaction. So 3-membered ring will be formed. Now dear students, I have explained the various saline features of the pericyclic reaction, how it is differ from other organic reactions. The most important differing points are the organic reactions required the intermediates, Carbanion cation or ionic intermediates or radicals, whereas in the pericyclic reaction they don't require any intermediates. The reaction proceeds via formation of cyclic transition state, and the reaction takes place in a concerted manner. So this is the major difference between the general organic reactions and the pericyclic reaction. Additionally, it does not require any acid-base condition, it does not require any polar solvent, it does not require any reagent or this added salts or the catalyst, except Diels-Alder reaction will be changed with the use of the catalyst. So these are the most important. The reactions also takes place thermally and photochemically, and as I told you that the thermally induced reaction will only give you the increase in energy, and the electrons will stay in the bonding orbitals. Only the energy will be increased and the reaction takes place in the thermally induced reaction, whereas in the photochemically induced reaction, the reaction takes place via excitation of the electrons from the singlet to triplet state. So here I forget that in the photochemical reaction state, maximum reactions are originated or takes place in the triplet state. Please remember. Why? Because the the life, it has a the life of this particular triplet state is longer than the life of the singlet state that we have seen in the Jabalinsky diagram. So this is all about the brief idea of the pericyclic reaction. This is the introductory part, but the most and the extremely important point to be noted over here, that what is extremely important. So I am talking about the extremely important point, that I am talking about the, to explain the pericyclic reaction, what is important? Explain pericyclic reactions. Pericyclic reaction, what is need? What is the, we must know how to draw molecular diagrams. How to draw the molecular diagrams. Molecular diagrams. So in the next lecture, I will teach you how to draw the molecular orbitals, how to draw the linear combination of molecular orbitals, various nodes, the symmetry, the conservation of the symmetry, etc., etc. Because without knowing all the details about the molecular orbitals, you cannot proceed for the mechanism. So in the next lecture, we will see the how to draw the molecular diagram. Thank you so much.